status word where we thought to explore different bits inside the 8-bit program status word or PSW. And we thought that we will ignore this registers for the timing like tcon, tmod, and other registers that we briefly discussed. We will come back to the details while doing programming part of it after completing the instruction set, after covering the instruction set. So again, the interrupt structure will come back a little later. So today, actually, I will skip certain slides from this PowerPoint. We will keep those slides for subsequent classes once we go deeper into the design part of it. Otherwise, if I just say explain this kind of slides to you right now, it may not be very relevant unless you know the programming and how it is connected to the software part of it. So we have started with the hardware connections, and we thought that we will cover some of the hardware, basic hardware issues for executing the code inside a microcontroller. So we'll review just, I think, 2 or 3 slides from this PPT, and then we'll move to instruction set. So this is the first slide that I wish to cover today. It is about reset and clock generation operations. So you have to make sure for normal operation of a microcontroller, the microcontroller should be outside reset state. That means reset should be deactivated. But reset is necessary at startup. That means if you power up a chip, microcontroller chip, then you have to apply an automatic reset signal. So this reset signal comes from outside a microcontroller and goes inside a microcontroller. Assuming this black box is the microcontroller with some pins shown, and this reset is the signal that comes inside. So that the arrow direction is looking inside over here through pin number 9 of the 40-pin version of the 8051 microcontroller. Now, at startup, why do we need reset? We need reset because the reset signal initializes the internal registers, some registers, and some other blocks inside the MCU chip or microcontroller unit chip. MCU is another short form of representing microcontroller unit. So reset, essentially the most important purpose of reset is to initialize the program counter at 0000 hexadecimal. Why it is needed? Because we want our code to get executed or start executing the code from 0000 location in the program memory, and that program memory is indicated by the program counter. So once we apply the reset signal, so program counter inside the microcontroller automatically gets into the initial value, that is 0000. Now, how to do this reset signal? We can either press a switch externally. Every time we start, we can press a switch or have giving logic 1 pulse over here. So there is, let's say I have some logic 0 voltage, and then I give it logic 1 for some time and then come to 0 again. So it could be a little square wave signal applying as a reset immediately after power up. But in order to make this automation automated, we can use this CR combination. So if you look at this capacitor and the resistor, so ignore the values for the timing, but you can calculate time constant based on the values. So the moment you turn on the switch to VCC, that means you are applying VCC with respect to ground. At that time, so this VCC is also like a unit step waveform, right? So it's like a step waveform. So unit basically depends on whatever voltage. If it is 0 to 1 volt, we can call it a unit step. But if maybe 0 to 5 volt, 0 to 3.3 volt, after you turn on the switch of VCC, that means battery connection or power supply connection. So the moment you apply VCC, so this C comes first and R comes next, and then ground is connected. So this CR circuit acts like a high pass filter. That means you are giving a rising edge of a digital signal due to power on process, and due to that rising edge, this capacitor momentarily shorts. So that means VCC is applied over here. So at this middle terminal where the C and R are joined. And this middle terminal gets a little spike of VCC. It's like a differentiated value or differentiated version of VCC signal, because this is a high pass filter. High pass is also known as differentiator in analog electronics. So this differentiated spike or pulse will come and then gets applied to RST. And then once the capacitor gets fully charged after some time, based on the time constant that you are selecting for through the values of C and R, this capacitor, the lower terminal voltage, basically after some time when the capacitor is fully charged, this terminal voltage will become logic 0 or close to 0 volt. So then reset pulse is automatically removed. Now if you power off VCC again after some time, let the capacitor discharge through self-discharging, because practical capacitors are having leakage inside. Then afterward, again, if you restart your VCC, again one RST pulse will come. So that means every time you power up, one little spike-like signal or one single pulse kind signal will be applied through reset. And once the reset comes, program counter goes to 0000X. And also another thing happens at power up. So you can operate the crystal. So this is the symbol of a crystal, and this crystal along with these two capacitors and some internal circuit inside the microcontroller forms a crystal oscillator circuit. So that is a square wave oscillator circuit where the clock frequency at the output of the internal oscillator will become the crystal frequency, which is it may be 4 megahertz, it may be 2 megahertz. Here it is shown as 11.0592. So this is one of the standard values that are available, that is available in the in the market. So this reset operation is absolutely essential, and you should not avoid this step. And this connection is also necessary apart from VCC and ground connections to the microcontroller. So these are some very basic level connections which are required. Now another in this particular slide, I'm trying to show that how an external program memory is connected. Suppose you have written a code for the microcontroller which is having the length or size more than 4 kilobytes, because inside the microcontroller there is a 4 kilobyte of ROM or flash if it is 8/9 series. So beyond 4 kilobyte, if you want to store your program, then you have to use an external memory, an external non-volatile memory. It may be a flash or EEPROM or EEPROM or any other types of non-volatile memories which might be available or and also compatible. So how do we connect that external memory if we want to do that at all? So the way to do that, you have to connect the address lines and data lines. So that is compulsory, and also control lines, some control lines. So if you remember from the data sheet that we considered the pin diagram from the data sheet, port 0 was having 3 functions, standard input output functions through port 0, and also address 7 to address 0. So all 8 bits can be either address pins or data pins D7 to D0. Now, using this latch, so there is another D-type flip-flop array. This is 8 D-type flip-flops which are outside the microcontroller chip. So this is a chip like 74373. We'll see the details, and we had seen also in one of the slides earlier. 74373 is a 8-bit latch. So we can use this latch, and the clock for those 8 latches or flip-flops is controlled by the ALE. This is address latch enable. So this is a clock signal for the flip-flops inside this particular block. So you can connect this AD7 to AD0 or P0, all the lines from P0 port directly to the data pins like D7 to D0 pins of this external non-volatile memory. And just take a tap, just take a parallel connection from this point, and then give it to the input of the latch, and then the output of the latch is called as A7 to A0. So here, what we are doing, we have a multiplexed signal, or it's a time multiplex address and data signals coming out of port 0, and you're taking just parallel connection to 2 different paths. One of these paths is directly going to data pins. So this is a bidirectional data pin or data port inside the EEPROM that has been shown, and the address lines are going through the latch signal. And now address lines are unidirectional, data lines are bidirectional. Okay, so that's why the bidirectional signature sign is shown over here. Now, regarding the other address lines, because the 8051 can address 16 bits or 16-bit memory, or that means there are 16 address lines. So 16-bit memory in the sense 16 address lines I'm trying to say. So your memory could be either 8-bit width or 16-bit width or 32-bit. In 8051, we are considering whatever memory inside this EEPROM is there, they are all 8-bit wide. Okay, but addresses are 16 bits. So remaining 8 lines beyond this A7 to A0, which are A15 to A8, are coming from the P2 lines, P2 port, because P2 has an alternate function of giving this address lines. And now the program store enable, it's a kind of output, active low output signal, which is going to the OE bar or read bar, you can say. So this is output enable bar. So this output enable bar is a kind of chip select. It's kind of enabling this EEPROM. So in addition, you need the read bar signal. Okay, so that is also another signal that might be used over here, but that is optional. PCN is absolutely necessary because EEPROM is a non-volatile memory. So that means we must have programmed it once, and then every time the program instructions for the program are coming to the microcontroller must be coming from the memory inside this EEPROM and going towards through the D7 to D0. It's always going inside P0 port. Okay, so data is always unidirectional in this case because we cannot program during runtime this particular non-volatile memory. So this is how we access the external program memory. But one important thing is the EA bar must be ground. So EA bar is an input signal. So external access is enabled if you put this EA bar to logic 0. So by connecting to ground, we are putting it in logic 0. Now, in addition to this interfacing connections from this address data pins as well as control lines or pins, we have 2 more ports like P1 and P3. We don't need them for address data or control signals. So you can use them separately as normal input output ports like serial port or parallel port or any other timer kind of applications from the other 2 ports. Similarly, we can have a data memory access. Suppose we have 128 bytes of RAM, internal RAM, but we need additional RAM space for storing our data. So in that case, what we should go outside the chip for accessing data space. And this is with the assumption that we have already programmed the memory, the non-volatile memory, ROM or flash, and we don't need more than 4K. So assuming that fact is true, our program is less than 4K. So we don't need an external ROM. So only internal ROM is enough, but external data is required in this case. So this is the just opposite case as the previous case for program memory. So in this data access, again, port 0 and port 2 are used for address and data lines. Okay, so port 2 we may not need the entire port 2. So there are 8 pins in port 2. So all 8 pins may not be used for address lines. So same thing is also possible here. Although I've shown A15 to A8, all 8 pins are used for address, but your memory may be less than 64 kilobytes. So if you have 32 kilobytes long memory, in that case, A14 to A8 is enough. A15 will be just cannot be connected because you may not have that A15 connection if the total size of this EEPROM is 32 kilobyte instead of 64. So this is the assumption that the EEPROM is 64 kilobyte. That's why all 16 address lines are used. But here we are assuming that we do not have again that much 64 kilobyte of RAM space, but we just need here 8 pins and then 3 more pins are shown. So this 3 maybe only 1 is possible if it is just 1 kilobyte flash. So sorry, if you have only 8-bit address lines, in that case you just have 256 location. If you have the ninth bit like A8 along with A7 to A0 only, then you will have 512 bytes of RAM. But if you are using this one up to A9, then you have 1 kilobyte, and then if you use up to A10, then that means the total RAM size is 2 kilobytes of memory. And if you can also add A11 to this, and then it will be 4 kilobyte memory. 4096 locations will be there, and so on. So you can keep on increasing the address lines, and then you will just keep on doubling the memory capacity. So that means 8-bit address line was giving 256, 9, just 1 bit extra is giving 512 bytes. Okay, another 1 byte, just double 1024 bytes, and so on. Yes, question.
Yeah, in the previous the program one, why have we connected the PSE and programs to enable to OE bar, and what is OE bar actually?
Okay, OE bar is an output enable bar, and PSEN is a program store enable, and this is again bar because active low. So OE bar is equivalent to an enable signal, output enable signal. Okay, so this is like a global level enabling signal. So it's like a strobe signal. If you have studied counters and other digital circuits, so there is a signal which there is an input to digital chips which enables the chip for subsequent purpose or its core purpose. So it's like an on switch, but it's not a power on switch, rather it's a system control on switch. Okay, so if you apply 0 from PSEN, which comes automatically through some instructions, at that time PSEN will go to logic 0 momentarily, and that logic 0 will get into this output enable. So this is EEPROM. That means it will only give out data during program execution. So during program execution, you have to make sure OE bar is logic 0, and that is actually controlled automatically by PSEN, and PSEN is controlled by certain program or instructions inside the microcontroller. Is it clear?
So PSEN is like a strobe signal, you say, right? So it does
it's like a strobe or enable signal.
It remains on when the reading has to be done. Like, is that it?
Yes, exactly. So you can see that through timing waveforms. We'll come to that later. Okay, and we were continuing with the data memory. So in data memory, basically based on your size of the memory, you can select the number of address lines, and same over here, based on the size of the non-volatile memory here, you can again select the total number of address lines, but the limit is up to A15 to A0, which is 64 kilobytes of memory. Here also, the limit is also 64 kilobyte. But if you don't need that many IO lines or for that many address lines, you can instead use the remaining lines from port 2, because there are total 8 pins here. You can use it for IO or input-output applications through your code. Now look at one thing. So here we are giving this read bar and write bar signal, which are multiplexed with port 3 lines. Some of the port 3 lines are used over here. And then read bar and write bar means whenever you are writing something to the RAM, then you should issue logic 0 to this, and while keeping read bar equal to 1. And if you're reading, then apply read bar equal to 0 and write bar should be 1. Okay, so either of these two should be enabled at a given time. And this signal, so read bar is going to the output enable bar, because you are actually reading something from the RAM. So when you want to read, so then it is OE bar, same as the previous case in the program memory case. So the data will be available whenever OE bar equal to logic 0 under reading mode. So that means through this data lines D7 to D0, data will go from the RAM to the microcontroller. Okay, while OE bar is 0. Alternately, when WE bar is 0 or WR bar is 0, basically on the microcontroller side, so you are writing data something to the RAM memory. That means you are putting something on P0 or whatever D7 to D0 pins, and then it goes inside the RAM. So this arrow direction is valid. So it goes inside the RAM, and once the where it will go, it is determined by the address lines. So based on the exact address value, and that will be decoded inside this RAM, and then there will be one single 8-bit location somewhere inside this RAM chip, which will get selected, and then writing will happen to that one very specific address location where 8 bits are present. So data memory should also have 8-bit wide, which is same as the data bus. So this is a traditional way, but not necessarily. I will tell you through programming that it's not necessary every data is only 8 bits. So some data could be 16-bit also. But in that case, we arrange that one after another. So that means two 8-bit locations, two subsequent 8-bit locations will be used for storing those data or reading from two consecutive locations. So that is possible. In 2 steps, we have to do that. That means we have to do apply 2 different addresses for those 2 locations, one after another. There will be 2 address latch enabled, so it is time consuming. It will take just double the time if you want to read or write 2 bytes instead of 1 byte. Okay, but it is always in group of bytes. So one you cannot do bit by bit writing or reading operation from both from the program memory case or and the data memory. It's always a chunk of 8 bits at a time. Okay, even if your data may not be valid for 8-bit, let's say 4-bit data is there, but you have to do read or write in 8-bit chunks. And if it is obviously more than 8 bits, then one after another 2 bytes must be accessed. And then P1 is free to for any other application, and as I said, remaining bits from P3, like 6 other bits, can be used for normal input output operations, as also possible with remaining pins of P2. So basically, higher priority is the address lines from P2, and remaining lines, it's up to you as per your necessity. Now look at this. EA bar is equal to VCC over here, and PACN bar is not used. So that's something to be observed. So external access bar is VCC. That means external access for program is not allowed over here. So program is, that's why it is in internal ROM only. You must restrict your program within the internal memory, non-volatile space. And EA bar is VCC, means disabling external access for programming. And PACN is automatically ignored. Even if you connect it somewhere, it is not going to have any signal on it. And you have to make sure you should not wrongly connect PACN with OE bar of the RAM. So that is another consideration. So, so given this kind of diagram, we had earlier discussed with the, let's see where it is. One sec, I'm going to. I'm trying to pull out the older slide. Where we had discussed something similar through this particular diagram. Okay, so initially, so we had seen this diagram at a very early stage. Now look at some similarities what we just discussed. So 87, those port 0 and port 2 are basically over here, and they are connected. So whatever number of address lines you need, you just take out those many lines and ignore 8, 13, 14, and 15 over here. This is the address latch enable that was used. So ALE goes to LE signal, so which is basically the clock signal over here for this particular LS373 chip, which is an octal latch. And OE bar, so this is basically output enable bar. This is another sort of strobe signal or enable signal, which is always connected to ground. That means this chip is always enabled. And AD, basically you take the data part of it and then connect it to the basically whatever peripheral you have or whatever RAM chip you have. You can share the data bus among multiple peripherals or memories, because but any one will of this memory or input output device will transfer data through the data bus. And then you have connected chip enable bar through some logic signal like A15. You have to configure this through program, then only this will work. And then chip select. Chip select is basically you are selecting the chip. It's like an enable signal. But in addition, so this is chip select is a master enable, whereas write enable is the whenever you're writing something to this chip, RAM chip, then only write enable signal should come, which is coming from WR bar. You can see WR bar is going to write enable, and RD bar is going to OE. So RD bar and WR bar are all output lines for microcontrollers, and input line for the RAM, random access memory. Okay, so in addition, so CS and CE bar, these are two additional controls which are given just to make sure that you have two-way control. Multiple microcontrollers may be present, so in that case also you can have some control, or through some logic combination you have to enable the entire chip. Okay, so one is active low, other one is active high, and remaining part basically just based on the design, how you are selecting the LCD module. So enable E is the enable module, so it is similar to chip select or chip enable kind of signal, but name is different for different modules. So for that, so you have to make sure that whenever RAM chip is enabled, LCD should be disabled in the data lines. So the data lines for LCD must be disabled. So that is possible through this read, write, and enable and register select. There is a RS signal. So we'll see that later on. Okay. So any question over here?
Sir, in the second port, are only the last 5 of those pins optional, or can I not use any of those P2 ports for addressing, and I can use all of them as the general input-output port?
You can definitely use every pin from P2 as input-output if you don't need them. If your RAM space is up to 256 bytes, then you don't need any one of this. Okay, so you can completely use it as I/O.
Okay, sir. Thank you.
Sir?
Yeah.
Would EA bar pin be software control, or we just need to provide hardware signals?
Your voice is, please say loudly.
Sir, is EA bar pin software controlled, or should only hardware bound signals should be sent out?
Oh, okay. So EA bar is an input signal which is a hardware controlled. Okay, and this hardware signal may come from another microcontroller. It may come from a switch. It may come directly from a connection, like permanent connection to VCC or ground. So this is a hardware signal. So EA is a hardware input signal, EA bar.
Okay, sir.
Okay. Then we are going bit closer to programming part, and that's why this ALU capability is very essential. You need to take care of ALU capability. Yeah, question?
Sir, I am asking once again, sir. EA bar is only for programs, program memory, right?
Yeah. EA bar is only determining or controlling the program memory location. So
Okay.
EA bar equal to 1 means internal memory of internal ROM is used for program memory,
Yes.
and EA bar equal to 0, that means external ROM or external non-volatile memory is used for program
Yes, sir.
memory. So this is only related to program. So
Yes.
where is the location of your actual code?
Yes, sir.
Okay.
Thank you, sir.
So ALU capability, basically these are some of the features of the arithmetic logic unit inside 8051. So you can see I have written some thing in the short form. So these are all instructions coming from the microcontroller datasheet or detailed instruction manual or hardware manual. So it can do addition operation, it can do increment operation. So increment means add by 1 actually. So add by anything up to 8 bits is this instruction, and then increment is add by 1, and DC is decrement by 1, that means subtract 1. Then compare if 0 and compare if not 0, CMP-Z and CMP-NZ. So these are some instructions. We'll see the syntax of these instructions. You have to remember the syntax and how to use it. Also addressing modes, so I'll talk about that in a moment. Then subtract with borrow. So SUBB is a subtraction, 8-bit subtraction with a borrow, and there are rules basically which values you want to subtract and where should be the result location, and all those things are there. Similarly, you can see mul is multiplication, and div is division operation. So these are some arithmetic operations the 8051 CPU can do. Then logical operation, ANDing, ORing, XORing. Then RL is rotate left. Rotate left is basically you take 8-bit number and just rotate it by one position towards left. Basically, you just copy everything, shift it by one location, and then paste it back to the same register. So typically accumulator is the register. So rotate left, and then rotate left with carry. So this is a 9-bit rotation, and this one is 8-bit rotation. Okay, so rotate left with carry. That means you consider carry bit, which is in PSW, along with this rotation of the accumulator. Similarly, rotate right with carry. And then there is a swap instruction. Swap is basically 4-bit operation. You have an 8-bit number, and you just split that 8-bit number into two 4-bit numbers side by side, and then copy and exchange them with their locations. So bring the right hand side 4-bit number to the left hand side of the register, like accumulator, and whatever was that originally in the left hand side, copy that and store it in the right hand side of the accumulator. So this is a swap instruction, typically 4-bit swapping. Also, there is a bit level operation. So typically it's called as Boolean operation or Boolean processing operation. So this bit level operations are there, such as you can make any of the bits 1 or make any one of the bits as 0. So making a bit 1 is set bit, and clearing means resetting bit, or 0 making the bit 0. These bit operations are possible only to certain registers in the SFR. If you remember SFR, yeah. So this bit addressable registers like accumulator, B, PSW, and whatever is listed in this particular column are only compatible to those Boolean operations. Okay, and rest of the registers are not supporting this kind of Boolean operations or bit level operations, like bit level changes or processing operation. So set, reset, complement. So you can, if it's like a NOT gate, so you can just make it 0 to 1 or 1 to 0. And then there are some conditional instructions which are very, which makes the processor, any processor, more powerful than the basic operations like logic and arithmetic operations. So these are conditional instructions. So there is jump, if, set. So if certain bit is logic 1 initially stored with logic 1, then jump to another location within the code, and jump if not set, and jump if set and then clear. So if it is set, then only you jump, and make sure that you clear it off after jumping, so that subsequently someone else can make it set if necessary. So these are some conditional instructions. In addition, there are call instructions also which are present. We will see that in detail. So these operations can be performed on the part of the data RAM. So basically what I'm saying that, so this bit addressable registers so are only compatible to this kind of Boolean operation. So that means only perform on the part. So not all the RAM locations are compatible with Boolean operations. So you have to keep that in mind while writing code. So these instructions, whichever will come in this category, are only under bit addressable registers only. You can do that with bit addressable registers. Okay, so that means within the general purpose RAM, certain locations are bit addressable and certain locations are not actually bit addressable. So there are you have to always keep that in memory, that about this limitation or feature. Obviously, you don't have to remember these addresses where exactly this R0 to R3 R7 are located and so on, but only make sure that you are actually considering the locations through your code correctly, and these addresses are automatically taken care of by your compiler or assembler, given your syntax is correct or your application of the instructions are correct. So there are different basically registers which are mainly compatible with bit. So this is basically a summary of the accumulator, serial control, timer control, all the port pins. Then B, actually, sorry about the repetition. A is actually accumulator. PSW, interrupt priority and interrupt enable. So these registers you have to particularly remember for bit level operations. Okay, so I'll just ignore these things. And then I will straight away go to the hardware manual for the microcontroller. Okay, so this is, you can download it from Microchip's website. I will also upload it in MS Teams. This is the most authentic document that you can refer for programming the microcontrollers. So in industries, we always refer to such documents very on a routine basis. So this is for 81 series, 8051 series microcontroller. So Atmel never manufactured this particular traditional 8051. So that means they are compatible with MCS 51 series and like 8951, 8952 and so on. So this document is quite large, 116 page, but we don't need to go to that extent. We just need to go from page number 1 to 24. Basically this first chapter, section 1. Okay, so this instruction set, this 24 pages must be understood and studied by you. So this is a requirement in the course. And this document is very comprehensive, very easy to understand also, and to the point. So no extra information is given, just whatever you need, and the correct information has been given. So again, this document starts with the PSW. So PSW we have already covered, so there is no need to spend time here. So PSW format, so this is the 8-bit register with that carry flag and auxiliary carry, user flag, then register select 1 and 0, overflow and parity. So we have covered this kind of this particular thing. Actually, I got it from this document in this slide window. So whatever register informations are there are from this document only. Okay, because this is the most authentic document. And another thing that we haven't covered, but very, very important, unavoidably important, is the addressing mode. So let's start with the addressing mode carefully. So you have to understand that while writing any program, we issue instructions. We write instructions. Instructions means what? Different lines of the code. Okay, in assembly domain, so there are different lines of code. So you can do programming in two ways. Either you can do high-level programming for a microcontroller like C or C# or some Java kind of coding. Typically C, C++ is very common among all the high-level programming languages for microcontrollers. And for that, it is actually quite easy. In C kind of syntax, we have to customize our C program for certain hardware configurations. So basically, you can use printf, scanf, and all those information, all those basically syntaxes, but it must be compatible to your hardware. So while writing an embedded C code, your mind should work in the background that, okay, what is my hardware, how it is going to perceive this code. So you have to understand that relationship between your code and the hardware or the processor that is executing in the background. So another way to do that is addressing mode through assembly level coding. So assembly level coding is basically a low level coding, relatively low level coding. So unlike C, C is a high level language or high level coding. So in assembly language, like INC and all those things that we had seen in the slide, add, MUL, mul, div, all those instructions are coming from the assembly level coding or assembly level programming strategies. So assembly level programming strategies still exist for each and every microcontroller, even it is ARM or RISC-V or any you just name any other microcontroller. Always there is some instruction set which are meant for assembly level coding. Now people typically don't write, if you see talk to developers, they generally go for high level languages. Why it is so? It is easy to write high level programs because you need very little or relatively little knowledge or less knowledge about the hardware, what the hardware is doing. So while you were writing C code in the past, have you considered how that i7 or i9 processor is executing that particular code? You never bother to do that, right? So that's why school kids can learn those things very quickly, because you just have to have a very narrow vision for writing. Just learn the syntax and practice a bit, and then that's all. But here we wanted to become an expert in this kind of embedded systems or even computer development. Hardware software correlation must be understood in the process. So assembly level coding helps you to have a very fine tuning certain code, and also helps in time efficient code execution. So the best of the programmers, they always do a combination of high level and low level programming. That means a combination of C and assembly. So these two types of programming goes hand in hand, and this kind of strategies are adopted by very expert programmers, because they understand how the hardware is doing the or executing the programs, and they just switch over between these two types of coding mechanism within the same big large code. So there might be several parts, some part in C or C++ and some part is in assembly. But if you write, you can ideally write everything in assembly, but ideally you cannot write everything in C. So that is another thing, because in assembly you will get certain special privilege about working with the hardware and knowing the hardware in detail. So for assembly like coding, these addressing modes are very, very important. Actually, these addressing modes are super important for assembly level coding, and it actually helps you to determine how you are producing the data and the program to the microcontroller's internal instruction in decoder and all those internal blocks inside the microcontroller or microprocessor, that how you are producing the data and the program lines to the microcontroller, such that you can actually understand how how many clock cycles each microcontroller program step or each instruction is going to take. I'll repeat. Why we need to know addressing mode? Addressing mode typically tells me that how we are applying the addresses for the data or the program parts to the microcontroller. As a result, we have a better understanding how much time the microcontroller is going to take per instruction. Okay, so this is very important, which is never possible in C. While we write one thing in C, let's say one statement in C, so I don't know after how many clock cycles that will get initialized. It might be predictable, it might be within some range, but exact number of clock cycles is unknown. Whereas in assembly, it is exact number is known, and it is possible due to this addressing mode. Okay, so that's an introduction. So let's look at this addressing modes supported by 8051. So first one is the direct addressing mode. So direct addressing mode means you actually provide address along with your instruction. So we have instruction mnemonic. So instruction comes in two parts. Okay, first part is the mnemonic of the instruction, like ADD, SUB, MUL. So those kind of things are called as mnemonic of the instruction. But there could be operand of the instruction, which is basically the data given or address given after that mnemonic. Okay, so the operand could be either address, it may be data. Two types of operands could be possible, and operand only comes with mnemonic. But mnemonic can come alone. So there are instructions where there is no operand, but only mnemonic is there. Mnemonic is compulsory for any instruction, but operand is like assistant to the mnemonic. Okay, so this operand may carry some address value, it may carry some data value. Now that address may be 16-bit or 8-bit, data may be 16-bit or 8-bit. Okay, in 8051 at least. So the operand could be 8 or 16-bit, both address value or data value could be possible and that operand. Now in direct addressing mode, so the operand represents 8-bit address. Okay, so there you have seen certain SFRs are given with 8-bit addresses. Okay, so those addresses, if you write directly with your mnemonic, let's say add then comma some 8-bit address. We'll see the format in much more detail. Add a comma something. So this kind of instructions will come, and then that something means 8-bit address. It may be 8-bit data and so on. So based on that, if the 8-bit address is provided, then I call that as a direct address. That means directly you are providing the address of the register or a memory location. So you are directly providing the addressing. In other case, so there is an indirect addressing. Okay, so indirect addressing means it is you are again you have to definitely produce or provide an address. Where is the next data? But for that you are doing it in the indirect way. Okay, indirect way means you are not writing it all with the instruction, as in the first case in direct addressing. Here we are writing this address 8-bit, but here instead we are specifying a register. So that means I can store my address in any one of those registers, R0 to R7 or anything, wherever applicable, whichever are applicable, obviously, based on the instruction, and that content inside R0 or content inside R7 or R1 or whatever is providing me the address. So the address is pre-stored inside a register, pre-stored by another instruction, previous instruction. So now once I have that address pre-stored, and now I'm pointing that, okay, you go and take the address from this register and do my addition or subtraction operation. Okay, so that is called indirect addressing mode. So these two are not the only one. There are many more addressing modes available. So you can see register instruction addressing mode, where you are actually controlling or you utilizing all the R0 to R7, so which can be accessed by certain instructions. So that means there are instructions you will see where the instruction automatically carries this name R0 or R7 or R1, so whatever these 8 names, R0 to R7. So instruction itself has this part already predetermined. So this is a customized instruction for this special function registers R0 to R7. And now by changing the bank, you can go to different R0 or different R7 or different anything in between R0 to R7. So that means for register instruction is typically referring to this R0 to R7 category, where the instruction itself carries this number or this identifier for the basically execution. So you can do addition where R0 is having a data. Okay, so that means so now you can pre-store the value inside R0 or anywhere up to R7 in any one of those 4 banks, where the data is stored inside R0. So in indirect addressing mode, address was stored in R0. Okay, but in register instruction mode or in instruction addressing mode, data is stored in R0. Okay, and now this data can be used directly. You can use the data to add, subtract, or do some logical operation and so on. Now there are another type of addressing mode called register specific. So now you can argue that register instruction is also register specific, R0 to R7. But register specific, they've kept the name separate because it belongs to another category. Okay, so it basically this accumulator or data pointer kind of category, where so there are certain special instructions apart from this R0 R7 category, which has even more features. So there are 2 to 3 features of can be done by using one instruction, but it is only limited to certain very limited type of registers, like A register or DPTR high or low kind of registers, or DPTR as a 16-bit register. Okay, so that is register specific instruction set or addressing mode. Then immediate constant addressing mode, so where you are saying that a constant number, so that is a data. Okay, so for example, in this example is given, so the number 100, so this is a decimal number. The microcontroller compiler will automatically convert into binary or hexadecimal. So this immediate value is given. So this is called immediate constant addressing mode or immediate addressing mode, where along with the instruction, so MOV is the mnemonic of the instruction, and A is the register that we have studied. This is a special function register, and then comma hash 100. So that means this value of 100, which is 64 hex, and you can convert into binary 0110 and 0100 for these 2 digits. So 0110 and 0100 directly goes into the accumulator register. So that means move destination comma source. Okay, your source is this constant number. This source may be any other register also. Okay, but in this immediate addressing mode, so you have the immediate value given. So this is a data which is immediately provided along with your instruction. Okay, and now you can think of one thing before going to indexed addressing mode. So you can I will just clarify one thing. Look at this move or move A is basically is one mnemonic, and this is the operand part of this instruction. So mnemonic typically takes 8-bit location. So that means you have to reserve 1 byte for storing this particular mnemonic, and for storing another 8-bit, which is 64 hex. Okay, so this 64 hex takes another 8-bit location. That means this instruction takes 2 consecutive locations in the program memory. So in the program memory, your mnemonic along with your data is present. Now, every mnemonic comes with an opcode. So opcode is like basically accumulator A is having some address, as I said in this SFR, sorry, in this here we had seen that accumulator A is having address of E0 and B is having some F0 and so on for other registers. So every register name is associated with some address, and address is the most important thing that is actually recognized by the microcontroller inside the microcontroller. So, so for storing, basically similarly for storing move A. So now I'm not talking about only A. I'm talking about move something to A. Okay, so this mnemonic comes with an internal opcode. It's like address for this kind of mnemonic of the instruction. So opcode is basically a code. It's a table. Opcode tables are there for each and every mnemonic. Okay, so there could be add mnemonic. So opcode is unique for add. So now there is a subtract mnemonic that is different opcode for that subtract. Similarly, for move A, there is opcode. Move B will have another opcode, and so on. Now the indexed addressing mode. So in this case, only program memory can be accessed with indexed addressing mode. See, this is having a restriction that you can address or access the program memory wherever it is inside the processor or outside the processor. The memory can be pointed by using either DPTR or program counter. See, DPTR has two parts, DPH and DPL. So combined together, 16-bit DPTR forms, and program counter is itself 16-bit, another register. Okay, for program memory. But for getting a 16-bit data from a program memory, let's say I have a table stored in the non-volatile memory, and there I can actually use data pointer as well, because data can be also permanently stored in program memory. That is all one possibility, and that's why you can use either PC or DPTR for this kind of addressing, where a 16-bit address is given. So how it is different than the previous one, this direct or indirect addressing? In this direct and indirect addressing, we were having 8-bit addresses. Okay, so only in both the cases 8-bit address fields were there. But if you use this index addressing, you can actually use 16-bit addressing. So that is the advantage of this index addressing. That means the entire 64 kilobyte address range is accessible through the indexed addressing modes or mode. Okay, so these are the 6 addressing modes which are considered or present in 8051 series microcontrollers. All 6 came originally from old Intel's design, and Atmel has just inherited all of them, and they've reduced the power consumption of the chip. They came up with smaller size of the chip and so on. But all these instructions and as well as this addressing modes came up from the original or traditional 8051. Okay, so do you have any question up to this point? So any question? No question? No question? Okay, so if you don't have any questions, so we'll stop the class here. So in the next class, we will start with the addressing or rather the different instructions from this document. You can study them beforehand such that you can ask me more questions about if you have any questions. So you just have to study this and just ignore. You can study section 2 for your better understanding, but this is not an absolute necessity. But this first chapter is an absolute necessity. Okay, so you can just before packing off, just a little thing. So instruction set basically comes with a in a table. So there are very large tables which are present, and you have to basically memorize the instructions. So there are very large tables which are present for every microcontroller. So since 8051 is a complex instruction set, that's why the list is very long. Okay, so this list is quite long, and you have to study all the instructions in detail. So it's better if you study start self-studying. We will cover in the class, obviously, from each and every group of instructions. However, it is always advisable that you also start studying these instructions beforehand. So you will find that there are all sorts of instructions like arithmetic, logic, and basically, sorry. So you will find this arithmetic instructions, logic, data transfer instruction, MOV 100, A, 100 that you had seen, it comes under data transfer instruction. So then there are instructions related to external RAM using data pointer. Then there are basically different lookup table related instructions, Boolean bit level instructions, then conditional instructions or simple branching instructions like jump. And then there are different types of instructions that you can see, and also you can see in the summary all the instructions at a glance. So look at this, just a very preliminary information before we start from next class. You will find that every instruction like add something to something, then you will find that how many bytes it is taking in the program memory and how many clock cycles it is taking to execute this program. That means if I apply my crystal frequency as 12 megahertz, then it will take 1 microsecond. That means 12 clock cycles into that period, 1 upon 12 megahertz, you'll find about 1 microsecond will be used. So by using this oscillator period, so you can scale or select your frequency of the oscillator frequency. Okay, so the crystal frequency can be chosen based on your analysis of your problem. So if your problem requires a faster operation, you should choose the faster frequency of operation, but number of cycles per instruction is going to be constant always, because for, let's say, I want to do subtract with borrow, it will always take 12 clock cycles, but there are instructions that takes 24 clock cycles or 48 clock cycles, like here XRL exclusive OR, it takes 24 clock cycles, and and it takes 3 bytes of data because of its format and so on. Okay, so we'll stop here today, and we'll continue our discussion in the next class on Monday. So any question if you have, or you can leave now.